Everybody now got a copy of special quiz number 1? If not, pick up. Is exam 1 a lot of fun? 13 points a question. Results will be up this afternoon. Key also, possibly. Just check Sakai. So we move on with the analysis from a pH determination standpoint. Water solutions, polyprotic, Bronsted-Lowry acids and bases. 3 subcategories, which we listed last time. Subcategory number 1, the parent acid is strong but molecular. The only common example that I know of is sulfuric acid, which we analyzed last time. Arithmetic for that system, on realizing that the first ionization reaction goes 100%, involves then calculations with K for the second ionization equilibrium established, which for sulfuric acid means Ka for hydrogen sulfate ion. Second case, parent acid is also weak. Molecular, but this time weak rather than strong. Number of examples of such in the acid-base table. Phosphoric acid, oxalic acid, conjugate base of phosphoric acid, H2S, quote-unquote H2CO3. And third category, which we'll tackle in a short while, the parent acid is weak, but a hydrated metal ion, which we'll see is the most challenging case of the 3. That's why we put it off to the last consideration of these 3 subcategories. Now, parent acid is molecular, but weak. We cited a number of examples. The formulas for such which are in our acid-base table. The analysis of quote-unquote H2CO3 solution is in the notes. We'll do something with that in a short while. But let's pick on a case which is not in the notes. Say, consider the hydronium ion molarity for 10th molar to 2 sig figs H2S solution. Here's the chemistry. There's the first ionization equilibrium. There's the second ionization equilibrium. By definition, for the first ionization equilibrium, K is Ka1 for H2S. The value is 1.1 times 10 to minus 7. By definition, for the second ionization equilibrium, K is Ka2 for H2S, which is Ka for HS minus. The value for this is an approximate value, and it's given in the acid-base table, 1 times 10 to minus 19. Why do you think this is an approximate value?
It's recorded, but it's so small. Where's the accurate reading, but it's so low?
It has to do with being small, but I didn't hear what you said before.
The accurate reading, but it's so low.
Accurate reading. Is that what you said?
Yeah.
Accurate reading of what?
Of the concentration.
Well, you remember, which we discussed a short while back, that if you're going to get K values, you got to go to the laboratory and make measurements. If I'm going to measure a K value, which is this tiny, what kind of concentrations am I going to be measuring? Concentrations which are daggone small. And the smaller the concentration, the more difficult it is to measure them reliably. That's why this is only an approximate value. Secondly, this ionization equilibrium produces sulfide ion. Can you produce a substantial molarity of sulfide ion in water solution?
No.
Hell no. Why not?
It's too strong.
It's a very strong base. So trying to measure the molarity of this stuff, given that it's going to be very tiny, is not easy to do, measured reliably. Now then, just for comparison, an appropriate conversation of such at this time: polyprotic acid, quote unquote H2CO3. Ka1 is 4.2 times 10 to the minus 7. Ka2 is Ka for bicarb ion, and it's 4.8 times 10 to the minus 11. I ask that you compare the value of Ka2 for this acid to Ka2 for this acid. Approximately 1 times 10 to the minus 19 versus 4.8 times 10 to the minus 11. Do you recognize the appreciable difference in these numbers? Both of these numbers are very small, but this number is huge compared to this number. Do you see that? This number is over 10 to the 8th bigger than that number. Hey, that's 100 million. That's a lot bigger. Why? Why is Ka for hydrogen carbonate ion so much bigger than Ka for HS minus?
It's easier to have carbonate anions in water than it is to have.
Easier. I don't like that word, but I think you're on the right track. Tell me what easier means.
More likely because it's a weaker base.
What's it?
The carbonate anion versus the sulfide.
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 That's it. As we will recognize in detail in chapter 23, when we talk about ways by which we can determine the strengths of acids and bases. We're not doing that now. Now we're just saying this acid has this strength as indicated by its Ka, or it's strong or it's weak, whatever. When we get to chapter 23, we'll talk about reasons why sulfuric acid is a strong acid and H2S is a weak acid. But just for the immediate moment. For this reaction to go, you got to pull H plus away from sulfide ion. For this reaction, for the reaction that corresponds to Ka2 for this and Ka for that, you got to pull H plus from carbonate ion. So as was just pointed out, the answer to why that K value is a whole lot bigger than this K value has to do with the fact that this base, which is minus 2, just like this base is a lot less reactive, a lot more stable, a lot weaker than this base. Do you think that this might have something to do with negative charge density? That's exactly what it has to do with. The greater the negative charge density of a species, the more strongly it attracts anything plus. End of story. From a Coulombic standpoint. And when you attract H plus, that's all you're doing is attracting a positive charge, because H plus is just a bare nucleus. So there cannot be any electronic interaction with electrons from H plus, because H plus ain't got any. All right? So I ask right now, what would you do to propose an explanation of the weakness of this base? What would you do?
The carbonate ion is so much larger than the sulfide, and to the same charge, the density is going to be much lower. And
all right, can you go further with this? What is the most important property of a species?
Structure.
Let's see the structure, please. Right now, Lewis structure, carbonate ion on your paper. Let's go. Clock's running. Everybody get this? You have to be able to write Lewis structures for these simple species. Boom, zip. You need to practice. What you need to know is in chapter 23 of the notes. I've reminded you now several times about this. Did you see any questions on exam 1 which had to do with structure? You think you'll see questions on coming exams and quizzes which have to do with structure? If you think not, you might as well just leave now. Hey, it's the most important property of species. So we will focus on that property of species throughout all the time, as you must do in any chemistry class. Real chemistry class. Chemistry classes which don't pay attention to that, I don't know what the hell they are, but chemistry classes, they ain't. How about that for an attitude? All right, now tell me, do you believe that the negative charges borne by carbonate ion are borne by the 2 singly bonded oxygens, as the Lewis picture suggests? Do you believe that the carbon-oxygen bonds in carbonate ion are 2 which are weaker and longer and 1 which is shorter and stronger? Do you believe this? That's what the Lewis picture says. Do you believe it? Why not?
Resonance.
Resonance. What's the structure of this species? I mean shape, pardon me. Trigonal planar, isn't it? The carbon atom is how hybridized?
SP2.
SP2. Tell me, to make pi bonds, what kind of orbital overlap is required?
Top bottom hybridized p orbitals.
Hybridized p orbitals.
Unhybridized.
Unhybridized p orbitals. Can you draw a picture of 2 p orbitals engaged in strong pi bonding? Can you draw that picture on your paper right now? 2 p orbitals, an illustration of pi bonding between 2 p orbitals. Strongest possible pi bonding. You did this in 45, now let's put it to use. Let's apply chemical significance to this consideration. What's a p orbital look like? I'm listening. Some people describe it as a weightlifter's dumbbell. I like to call them 3-dimensional figure eights. Kind of like that. 3-dimensional. Not a flat structure. These lobes have volume. Whereas the second p orbital relative to this p orbital, if the p orbitals are engaged in the strongest possible pi bond formation with each other. The other p orbital over here? Is it like this? What kind of overlap is this? Sigma. Did you learn that sigma overlap means how many overlap regions? 1. That's a sigma overlap. that good pi bonding? No. How about that? Yeah. Which means, if you have effective pi bonding between p orbitals, the lobes of the p orbitals must be how oriented in space relative to each other? Mutually parallel. That's right. Just like that. So if this is an atom, and it has a pz orbital, because in chemistry, this direction is z. I know in math class this direction is y. I don't know why. Because here it's z. Who cares? It's arbitrary. What is the significance of Cartesian coordinate reference axes? Geometric significance. It's three straight lines which intersect at a place in space called the origin. And what geometric property do these straight lines show with respect to each other? They are mutually perpendicular, right? They make 90-degree angles with respect to each other. And how many p orbitals are there at a p orbital sublevel? 3. How do the lobes of these p orbitals orient in space relative to each other for the p orbitals of a p orbital sublevel? Well, orthogonal from an overlap standpoint, but that doesn't tell me geometric orientation. The lobes are mutually perpendicular. So, to refer to this, we use the handy Cartesian coordinate axis reference set and say one p orbital is oriented this way. What direction do you wish to call this? X. Now, as I said in chemistry class, this winds up being the z direction. We'll talk more about that later on. Which means by default, this direction is which? Y. So you got 3 p orbitals. One labeled px, because the lobes are on the x-axis, skewered directly through the center by the x-axis. One labeled py, and the other one labeled pz. So if an atom makes a pi bond with a pz orbital, the atom with which it pi bonds must use its p orbital, which one? Px, py, or pz? Pz. Because these are the orbitals from the atoms which are bonding with each other pi fashion that have the lobes mutually parallel. Can the p orbitals for carbon, oxygen, oxygen, oxygen for this species have the lobes mutually parallel? What is the geometry of this species? Trigonal planar. The picture I have on the board shows you the sigma system. This is sp2 hybridized. Here's a sigma overlap here, sigma overlap here, sigma overlap here. If I wanted to draw a picture of the pi bonds, a part of which is at each and every carbon-oxygen bond site, I'd have to be able to draw orbital lobe projections which are coming out from and going behind the board. That ain't easy to draw. But if I take this and imagine that the wind blows it till it's like this, then I can draw these p orbitals. Carbon, oxygen, oxygen, oxygen. And that is a pictorial illustration of the resonance property which carbonate ion possesses as a consequence of pi bonding at each carbon-oxygen bond site. All right? This is really a look to the future. But since I've now talked about it, you think I'd feel at liberty to ask questions about this on coming quizzes and exams? You're damn right. Now then, next question. What is the actual carbon-oxygen bond order? for carbonate ion? What is it?
1.33.
Call it 4/3. Okay? 1.33 is fine. 4 bonds at the 3 bond sites. Bond order is determined by, for the number of bond sites in consideration, you add up the number of bond pairs shown by the Lewis picture, that's 4, and divide it by the number of bond sites you're considering, that's 3. Next question. What is the actual formal charge on each peripheral oxygen atom for carbonate ion? The actual formal charge on each peripheral oxygen atom for carbonate ion. What is it? It's minus 2/3. You agree with that? Because what we recognize is that the valence electron environment of each oxygen atom for the carbonate ion is the same, which the Lewis picture can't show you. But understanding resonance not only shows you, but tells you. So you've got to see that part in your mind's eye. So what we're looking at here is a total charge of minus 2 borne by 3 peripheral oxygen atoms. Well, minus 2 divided by 3 gives us minus 2/3 formal charge per oxygen. So if H plus approaches this guy, he's really looking at a minus 2/3 attraction. Ha ha! But not this baby. This baby is minus 2. So the charge concentration on this is huge next to the charge concentration on that. Now then, back to this. We talked about this. Now let's get on the arithmetic significance of Ka1 being much, much greater than Ka2 when it comes to calculation of the hydronium ion concentration. Any of you recall what I told you about doing this? What arithmetic do we do to get the hydronium ion concentration for a water solution of a polyprotic bronze telluric acid which is weak and molecular? What arithmetic do we have to do? Ka1, and that's it. The numbers show you this. These very tiny Ka2s mean Ka2 ionization ain't going no place next to Ka1. So for the 10th molar H2S solution, here's Ka1. And if the second ionization equilibrium doesn't mean anything, then this can be read as x squared over m sub I minus x. All right? Now we talked about why this is valid, because Ka2 is so small it doesn't go anyplace. Ka2 ionization doesn't make a contribution to the hydronium ion molarity for the solution. So I wind up getting hydronium ion molarity of 1.0 times 10 to minus 4 for my 10th molar to 2 sig figs H2S solution. Well, that leads us to this question. For our 10th molar H2S solution, what is the sulfide ion concentration? Now, while you're thinking about that, I'll also ask, for 100th molar H2S solution, what's the sulfide ion concentration? For 1 molar H2S solution, what's the sulfide ion concentration?
Virtually 0.
I understand that it's virtually 0, but I want a number. Not virtually 0. I want an actual number, a non-zero value. I want to know the sulfide ion molarity for H2S solution, regardless of the H2S molarity. Given that H2S for such a solution is to be considered as the only solute. H2S solution. Well then, let's write Ka2. Is this okay? There's Ka2. And we have concluded since the numerical value for Ka2 is really tiny next to the numerical value of Ka1, that this equilibrium, this ionization reaction, number 2, ain't going to make any contribution to the hydronium ion concentration for the solution. Upshot of which is this relationship applies to Ka1, which is what we use to get the hydronium ion concentration. So, for any H2S solution, how does the hydronium ion molarity compare to the HS minus molarity? How does this molarity compare to this molarity? They are the same. So there's your sulfide ion molarity. It's Ka2. It's independent of the molarity of the H2S solution. How about that? Question. For any water solution of quote-unquote H2CO3, tell me the carbonate ion molarity. Tell me the number. I want the carbonate ion molarity for any water solution of this stuff as the only solute. I want the carbonate ion molarity. That's it. It's 4.8 times 10 to the minus 11. Isn't that Ka2 for quote-unquote H2CO3? Mm-hmm. It sure is. That means that will be the carbonate ion molarity. Which means if I take true carbonic acid, which is a much stronger acid than quote-unquote H2CO3. There's conversation about this in the notes. I trust you read it. If I have a water solution of true carbonic acid, and at the same molarity I have a water solution of hydrated CO2. This is a hypothetical case, because you can't have such. But if I were to have such, the hydronium ion molarity in the true carbonic acid solution would be much greater, as would the bicarb molarity be. But they would each have the same carbonate ion molarity because of what we just considered. Now then, the last part of this puzzle, since students are often concerned about this, and it's a reasonable concern for sure. How can I prove that Ka2 doesn't matter? So far we've just asserted such based on the fact that the magnitude of Ka1 is huge next to the magnitude of Ka2. Weak polyprotic molecular acid. How can I prove that Ka2 makes no contribution? Let's try a case. Let's go back to quote-unquote H2CO3. Given that when you dissolve CO2 in water, that's what you got. 99% plus. Okay? What I've done here is to show how we get the hydronium ion molarity based on Ka1 for 100th molar carbonic acid, hydrated CO2 solution. You can't get hydrated CO2 solution unless you got it under pressure more than about 200 molar. It's under fairly high pressure in carbonated soft drinks and beer. But when you take the cap off, then the pressure returns to normal atmospheric, which is why when you remove the cap from any carbonated beverage, out comes some CO2. Well then, here's Ka2 versus Ka1 for this quote-unquote H2CO3. We want to recognize the consequence of considering this to make a contribution to the hydronium ion molarity. There's the hydronium ion molarity based on Ka1. 6.5 times 10 to minus 5 for this solution. Following from x squared over m sub I minus x. Question. If Ka2 makes any measurable contribution Then the hydronium ion molarity has got to go up to become at least how much? Here's the hydronium ion molarity based on Ka1 alone. If this contributes to the hydronium ion molarity measurably, then this has got to elevate to at least what value? I'm listening.
10%.
Statement. If Ka2 contributes, H3O plus for 0.10 molar hydrated CO2 solution, because that's the solution we're considering, must be at least what value? I'm talking about the hydronium ion molarity for the solution. The hydronium ion molarity that will result. Here's what you got based on Ka1. If this contributes, whatever you wind up with has got to be bigger than this. So what's the smallest number, the two significant figure reliability, that's bigger than this? I'm listening. 6.6 times 10 to the minus 5. Because anything that's equal to or bigger than this but smaller than this is this. Which means Ka2 didn't do anything. And that's what we're about to prove. If the second ionization makes any contribution, it's got to raise the hydronium ion molarity from this value to this value or something bigger. But it's got to go up at least to this. All right? Now then, before the second ionization goes anyplace, what's the molarity for this? Remember, after the first ionization, but before the second ionization. See this? The molarity of this and the molarity of this are identical. 6.5 times 10 to the minus 5. Okay? And we're imagining the possibility of the second ionization making a contribution to the net hydronium ion molarity for the solution. So this is going to start as this. This is going to become this. Well, if the hydronium ion molarity went from 6.5 times 10 to the minus 5 to 6.6 times 10 to the minus 5, what's the carbonate ion molarity? What is it? It's that. Because this is the number I have to add to this number to turn it into this number. Right? And one reason I also wish to do this is because you folks need to start thinking about numbers and letting these numbers talk to you. And put away that damn push button device, which has turned you into an arithmetic cripple. We're going to get you past that. Our language is two parts. Alphanumeric. Letters and numbers. And if you can't speak the numbers part in science class, you're in one hell of a mess. And as long as you keep relying on that damn push button thing, you will not speak the numbers part. So don't rely on that. Unless I give you permission. For remaining quizzes and exams, I shall become an ethereal spirit. Or I will hover over you, all of you, each of you, while you're taking the quiz or the exam. And if I see you reaching for that push button device when you're not supposed to, I'm going to take out my golden harp and whap you. You got that? And if that ain't good enough, I'll take out my golden sledgehammer and smash that damn push button device. Because you see, if I thought the administration would let me get away with it, I would run this class with no pocket calculators permitted. How's that? Then you'd have to do it the way I want you to do it. And I would purposely design all calculation-based problems so that you could do them in your noggin. I'm going to design them all like that. 2 divided by 4. 0.2 divided by 4. That's when the sparks fly. 2 divided by 4, oh, that's easy. 2 divided by 0.4 or 0.2 divided by 4, and there, the confusion reigns supreme. Because I've been using that damn push-button device, and I don't want it. I don't want it for your benefit, not mine. I'm trying to make you good. You can be just as good, if not better than me, if you practice. Because I know many of you are blessed with more natural intelligence than I have, but I've been at this game for going on 45, almost 50 years. And guess what? I want to share with you as much understanding and experience as I have gained over all these 50 years in this one 3-month gathering. I want you to get from me as much as I can give you. But in order for you to do that, you got to do your part. Learning does not occur by osmosis. I cannot lay my hand upon you, and what I understand flows through my arm into you. If it would work that way, I would. But this ain't no game of magic. There ain't no such thing as magic. That's baloney. Doesn't exist. And so, what do we realize? If the hydronium ion molarity goes up at all because of the second ionization, then hydronium ion molarity has got to be this. The carbonate ion molarity has got to be this. And the bicarb molarity has got to be what? Come on. You can take 1.0 times 10 to the minus 6 and subtract it from this. Now you look at this. Because 6.6 divided by 6.4 is practically 1. Does 1.0 times 10 to the minus 6 come close to this value? Because this is the value that has to be satisfied. So this is screaming at us. 1.0 times 10 to the minus 6 is absurd because it's enormous next to this. Result, the carbonate ion molarity can be nowhere near that number for the second ionization equilibrium to be satisfied. Conclusion, second ionization equilibrium means not a damn thing from a numerical standpoint. In getting the hydronium ion molarity calculated correctly for a polyprotic bronze laurie acid, which is weak and molecular. All right? Now then, let's tackle one more case like this just to make sure you're adept at this case, given that this case is the simplest case. In the notes, there's a question posed for a phosphoric acid solution. It's question 1854. Phosphoric acid solution in question is 6.0 molar. Let's write the formula for this stuff in the structurally corresponding fashion. The Ka values for this, of which there are 3, are given in the notes, but Ka3 in the notes is wrong. Take it from the acid base table. It's 4.5 times 10 to the minus 13. So here's our Kas. I'll be damned I didn't remember this one. That's terrible. The question is calculate the phosphate ion molarity. All right, let's talk about the steps. To get the hydronium ion molarity from this solution, what will you do? To get the hydronium ion molarity for this solution, what will you do? You'll operate on Ka1 exclusively and treat it as x squared over m sub I minus x. All right? To get the molarity of this, this is what you get when the parent phosphoric acid molecule loses 2 H pluses. It's capable of losing 3, but after it's lost 2, you got that. What's the molarity of that? The value's on the board. Is this what you get after the parent acid has lost 2 H pluses? What do we do over there when the parent acid lost 2 H pluses? What do we do over with the hydrated CO2 when the parent acid lost 2 H pluses? We found out that the molarity of the species produced is equal to what? Ka which? 2. So the value for this molarity is this. And at a glance, you can recognize that the only way you can make phosphate ion in this solution is for Ka3 to do something. So let's write Ka3. 4.5 times 10 to minus 13 is hydronium ion molarity times phosphate ion molarity over HPO4 2 minus. This comes from x squared over m sub I minus x. This is 6.3 times 10 to minus 8. So at this point, how many unknowns you got? 1. The answer's in the notes. Solve it. We'll pick it up from this point next time, and I advise you strongly to read carefully over the next few pages in the notes, particularly about charge balance, because that's the fun part of the hydrated metal ion business that we will now have to consider.